Hello, my name is Camille Wong. I am a graduate research assistant here at Los Alamos National Laboratory, studying at the University of Oregon. Today I will be presenting on the method development of LC-MS-MS of eutectic bis 2,2-dinitropropyl acetate and bis 2,2-dinitropropyl formyl. This work is a collaboration between myself and my mentors, Alexander Edgar and Dolly Yang. Eutectic mixture of bis 2,2-dinitropropyl acetate and formyl is a 50-50 mixture of these two compounds on the right. This mixture is a type of nitroplasticizer referred to as NP for this presentation. The photo on the bottom right is a mixture of eutectic NP, which is used in polymer bonded explosives, PBX. NP is used to decrease the mechanical sensitivity of PBX while maintaining the energetic potential. There have been numerous reports questioning the thermal stability of NP, which leads to further examination of its use in explosive systems. In this study, we developed methods to analyze NP using liquid chromatography, tandem mass spectrometry, referred to as LC-MS for this presentation. LC-MS is a technique used to acquire molecular structure information. Using tandem MS analyzers in this way allows for better selectivity and sensitivity. To further examine NP's thermal stability, an aging study was done previously by my collaborators. The samples used for this study were obtained from that aging study. The aging environments used were air, nitrogen, water, and the aqueous phase from the water samples. These NP samples were aged from room temperature up to 70 degrees Celsius for up to 4 years. From the aging study samples, we learned that NP can diffuse out of the matrix it is in and can decompose at moderate temperatures. As a result of the decomposition, reactive byproducts such as NO, NO2, H2O, HONO, and HNO3 can form. Reactions such as oxidation and hydrolysis with these byproducts can further NP degradation. The gaseous molecules can diffuse out, but the intermediates are likely trapped in a closed system. This kind of system leads to an ongoing reactive environment. We also noticed in the beginning of developing an LC-MS method to analyze NP that residual NP material was shown in separate spectra of neat acetonitrile, acetone, and water, where NP signals should not be present. Therefore, a rinse method of the LC-MS system was needed to prevent from the contamination of the H samples and to ensure accurate results. The LC-MS method developed required to dissolve NP and dilute an acetonitrile in order to be analyzed. The samples were diluted in optimal grade acetonitrile 1 to 1,000 volume per volume. 1 microliter was injected for each NP sample, followed by a 10 microliter injection of acetone to rinse. The flow of the mobile phase was set at 0.3 microliters per minute, ramped from 10% to 99% acetonitrile. The organic mobile phase consisted of 0.1% ammonium acetate in acetonitrile, and the aqueous mobile phase consisted of 0.1% ammonium acetate in deionized water. The HPLC chromatography column was a C8. Followed by electrospray ionization in both negative and positive mode. For the mass spectrometer, the masses were collected from 20 to 650 mass to charge ratio, MZ. The data was collected in information-dependent acquisition mode. On the right is a figure of our LC-MS system, which includes high-pressure liquid chromatography with a C8 column, followed by the ionization source using electrospray ionization. Lastly, there is a high-resolution tandem quadrupole time-of-flight mass spectrometer. Here, we have the results of the system rinse test. This shows 10 microliters of acetone cleared the system of any residual NP. The top spectra is of NP diluted in acetonitrile before rinse. The red arrows are pointing to NP peaks. The red arrow farthest to the left, 330.09 mass charge ratio, which is BDNPF, with an ammonium adduct, and the red arrow on the right, 344.09 mass to charge ratio, which is BDNPA, also with an ammonium adduct. The bottom spectra is of a method blank, which is neat acetonitrile. This was collected after an injection of NP followed by a 10 microliter acetone rinse injection. The blue arrows are pointing to where the NP peaks would appear if present, but as you can see, there are no peaks at 330.09 or 344.09 mZ. This shows the rinse method was effectively removing residual NP from the system. Continuing with the NP results, in this study we chose to compare spectra of NP samples aged at 33 degrees Celsius in air for 2 months with NP aged at 64 degrees Celsius in water for 33 months. These samples were chosen to showcase least aged and greatly aged NP. The two spectra on the left show ESI positive results, and the area is in 10 to the 6th range. The two spectra on the right show ESI negative results, and the area is in 10 to the 7th range. These spectra are two different measurements of the same samples. When comparing the spectra, there are noticeable differences in the low mass to charge ratio range. These differences are representative of complex changes occurring during the aging process, such as reactions in NP, between impurities, and NP fragmentation. In conclusion, the system rinse was successful. Incorporating this rinse in the NP analysis method prevents samples from contamination and improves accuracy. But this rinse does increase the acquisition time. In fact, this doubles the acquisition time. The results from the aged NP analysis suggest the method is capable of resolving degradation products. This was done by using a wide enough range to reveal small molecules due to high selectivity and sensitivity with low background interference. In future work, we will continue to use this method to finish the analysis of nearly 4 years of accelerated aged NP samples. The results from the method will be used to validate and refine the NP degradation mechanisms proposed in previous works. This work will provide additional experimental evidence to guide the design of future aging studies involving NP. I would like to thank Charles Hills for programmatically supporting this project. I would also like to thank the participants and listeners of the Virtual Student Symposium of 2020. Lastly, I would like to acknowledge Dr. Casey Check, whose patience and understanding guidance led to and supported this work. Thank you. Does anyone have any questions?